Hi everyone, welcome back to another podcast or video lecture here for Managerial Economics. We're talking specifically today about profit and revenue maximization, and this is lecture 6 for us. This is a fairly long lecture, so we're going to get through it as diligently as possible here. So the first thing that we want to talk about in this lecture is the idea of optimal inputs. And so we recall that we assume labor and capital to be the only inputs in our single output production process. This in no way limits us to only labor and capital. We could include other inputs in our process, but we tend to just stick with this. We need a baseline to compare other input methods. So we can think of the total cost function in this way as the total cost, essentially. So we think of it as total cost is going to be some fixed value that we're choosing, and that's going to be essentially our budget. So if that's true, that we have some fixed total cost, it's going to be equal to the price of our input of labor, P sub L, times labor, plus the price of capital times capital. So if that's true, then what we could do is create, if this is true and total cost is fixed, we're on a budget, then we could do is create our ISO cost equation. And so for us, in order to do that, to create this ISO cost line, what we're going to do is solve for either K or L in terms of the other variable. So when we go back to creating this ISO cost function, so we can solve for K in terms of L. That would mean that we have TC naught minus P sub L times L is equal to P sub K times K. And then we have TC naught divided by P sub K minus P sub L, P sub K times L is equal to K. Here now we have the ISO cost equation that we were looking for. So we think of our budget, either be weekly, monthly, yearly, however we want to talk about it. In this example, we say the firm has a budget of $1,000. The wage rate is at $100 and rental price of capital is $150. So we can rewrite then our ISO cost equation to be beginning with this budget constraint. We then look to, in order to graph this equation, we need to solve for K in terms of L or solve for L in terms of K so that we're able to get K is equal to 6.67 minus 0.67 L. And so I think the method here is more important. And so in general, we solve for the ISO cost line to be this. And again, this is for K in terms of L. What we understand or what we see here is that there's a negative relationship. And this negative relationship between K and L is indeed linear because parameters P sub L and P sub K are given to us. So we realize that there's a trade-off between K and L happening. And this happens because of the inverse relationship. And we know that this relationship will be constant. This trade-off will be constant. So what does this look like for us graphically? So graphically, what we have is our budget constraint, so to speak, here. And this budget constraint is represented by our ISO cost line. So given this operating budget T sub naught and our input prices, we have a line, RAS, here. And this line, RAS, is essentially dictated by the slope P divided by L, P sub L, P sub K. And so our ISO cost line is important for us here. We notice that we can essentially change lines. So we can move in on our budget line to a new line TBU. So we have our new line TBU here. And so the reason that we have TBU is because we had to have had some sort of change in our budget. So it's clear that if we're moving our budget towards the origin, that we have a lower level of budget. So moving in means lower budget, moving out means higher budget or higher cost. What we notice is that between each line, though, there's going to be essentially the exact same slope, P sub L divided by P sub K. That's not going to change at all. So how could we change this slope of the line? Well, it would require us to not just change the budget, but actually change one of our input prices. So we notice here that, again, we begin with the line RAS. And so RAS for us has this slope, P sub L, P sub K, where now what ends up happening is that we had to have changed the price of labor here. And we can notice that notationally we've identified that we're changing the price. But how do we know what must be happening here? What must be happening at prices? If the isocost line is getting steeper in this way, it must be that the price of labor has risen. And I think that's important because it means that if we were to devote all of our resources into using labor, that we no longer could produce at S, but we would have to use the amount of labor at U here. And so we know that there is an increase in our, and we know there was an increase in our price of labor because of this. So let's go through a little bit of a problem here. Suppose that the wage rate P sub L is $25 and the rental price of capital P sub K is $40. In addition, suppose that the firm's operating budget is $2,500. So if we're looking at problem 7.1, we can start to record what we believe our isocost line is going to be. So TC naught is going to be $2,500. We have P sub L is going to be equal to $25. And then we have P sub K is equal to $40. So that we have 2,500 is equal to 25L plus 40K. So here is a good isocost line for this problem, and we can essentially solve for K or L depending on what we need to do here. So what is the isocost equation for the firm? Well, let's get something in terms of K here. So we have 2,500 minus 40K is equal to 25L. So let's divide everything through by 25. So we get 2,500 divided by 25 minus 40 divided by 25K is equal to L. So we should get 100. And so we should get 20 over 12.5. And I know this could be reduced further. K is equal to L. But we're okay with that right now. So this is a good equation that shows a relationship between L and K, where L, if we were to graph this, would have to be on the vertical intercept, K on the horizontal intercept, where if we devoted all of our resources to L, we would have a intercept, y-intercept term of 100. And so we have a slope then of negative 20 over 12.5. So we could go and kind of talk a little bit about B and C as if though we're talking about labor. So if labor is graphed on the vertical axis, what happens to the isocost line if the wage rate increases? So if the wage rate increases here, what we'd end up seeing, or we should see, is that we would have this occur. That we would have a rotation in of our isocost line. And if capital is graphed on the vertical axis, if labor is graphed on the vertical axis, what happens to the isocost line if the rental price of capital falls? Well, I think that this is interesting here because we have to just be careful a little bit with how we defined our total cost function. So we had total cost sub naught is equal to P sub L times L plus P sub K times K. And so we have TC naught minus P sub K times K is equal to P sub L times L. And so now what we end up having is TC naught P sub L minus P sub K P sub L times K is equal to L. So what we see here is as we changed the L and we increased it, we not only shifted it down, but rotated it out as well. Now if we are just changing the price of capital, what ends up happening then is that we have a new L and K. This should be just like that. Okay, so just a rotation out. So we can move on a little bit here from this idea to now look a little bit closer as what combination, what is the actual optimal input for us now that we have this ISO cost line. So our ISO cost line is important. It tells us kind of the combinations of L and K that'll get us to our specific budget. What we realize is this line is made up of an infinite amount of points. That means there's an infinite combination of inputs that'll essentially produce this specified level for us, similar to an isoquant in that way. So recall that the slope of then an isoquant, if we're changing gears just a little bit here, the slope of that isoquant we realized was negative MPL over MPK. And so if we think about this graph, K and L, we had a picture something like this for our isoquant. Now we have the iso cost slope, which is written like this, P sub L over P sub K. Again, we have this negative relationship, so we have something like this. So we're graphing K and L in both instances here, and so for us, we think, well, let's just combine them together in some way. And if that's true, then we have something that looks like this. So we have K and L, the line, something like that. So this is our isoquant, and here we have our ISO cost line. So I think we look to the slides and we see that there's 3 points here. So we see points A, B, and C. And each point is going to represent something different for us algebraically. And so point A is interesting because what it tells us is that we're on our cost function. We're on our ISO cost line, meaning that we've exhausted our entire budget. We're using the amount of capital and labor that, given the prices of capital and labor, add up to our cost. What it also says is that we're on our isoquant, that we can essentially, we could make Q sub naught at A. We could also make Q sub naught at C. But the problem is, we feel is that we could do better. We could make more from the resources we have right now. And if we just think about this really quickly, if we moved in from point A to a new point right here, would we not be better off at this new point? Is it not higher up on our isoquant, and is it not within our budget? If this point exists and this isoquant exists like this, then it means that we should be allocating resources in a different way. So what we look at is the slope at point A or at point C, and we realize at point A we get this inequality happening, that the marginal product of labor divided by the marginal product of capital. So the slope of our isoquant is much steeper than the slope of our ISO cost line. And then at point C, the slope of our ISO cost line is steeper than the slope of our isoquant. So let's rearrange these two, A and C, and we rearrange them in essentially talking about it in a slightly different way, is that we want to now talk about the marginal product of labor per dollar spent on labor. So mathematically, it's the MPL divided by the price of labor. So what we notice here is that the marginal product of labor divided by the product of labor is greater than the marginal product of capital divided by the product of the price of capital. So in essence, what we're seeing here is that we're overusing, at point A, we're overusing capital, and that we should start devoting some of our resources to labor. And we realize that because of this greater than symbol. So this tells us whichever MPL divided by the input price is greater means that we should devote more resources to that. And so here, we should use more labor. Where at point C, we should use more capital. And again, that tells us that we should be using, we get a bigger bang for our buck out of the capital here. And so if these are true, and we go back to our, if we go back to our points, point A and point C, essentially we're moving this way on our budget. And so what we end up finding is that there's a point B. And this point B is unique for us. This point B tells us essentially that we will find that there's no gain from reallocation, meaning that we can't give more money to labor or more money to capital and be better off, and also be in our budget. And if this is true, then it has to be that the slope of our ISO cost line is tangent to the slope of our isoquant. And so what that looks like without any of the other isocosts or isoquants in there, something like this. So we have this tangent point at point B. And I think that's a very important part for us because we cannot be better off anyway. So we want to get to this part. This for us is optimal in a sense. So what can we do next with this information? So let's try and solve a problem here. So suppose that the firm produces at an output level where the marginal product of labor, MPL, is 50 units and the wage rate is 25. Suppose that the marginal product of capital is 100 units and the rental price of capital is 40. So we can look at this condition. So we're looking at the MPL over PL, and we want to look at that in relation to the MPK over PK. And so the MPL is 50 units, and the wage rate is 25, and the MPK is 100 units, and the wage rate is 40. So what we solve down for is we get essentially 2, and then 2.5. And so we can now include this symbol so that we knew from this point that the marginal product of capital per price of capital is greater than the marginal product of labor per price of labor. And so we know now that we should be using more capital. So we're not efficient. So this means we're not efficient because we don't have the equal sign. And if we want to be more efficient, we need to produce more capital. Okay, and so we have another problem here. And so we have problem 7.3, and 7.3 is going to go look at this in a very similar way. So we have a production function Q. Q is equal to 100 K to the 1/2, L to the 1/2. During the last production period, the firm operated efficiently. I think that's important. So we operated efficiently and used input rates of 100 and 25 for capital and labor. So P sub K is equal to 100, P sub L is equal to 25. What is the marginal product of capital and the marginal product of labor based on the input rate specified? So this is a very, I think, simple part of the problem in part A. So we have essentially dQ dL is going to be 50 K to the 1/2, L to the minus 1/2. And dQ dK is equal to 50 K to the minus 1/2. L to the 1/2. And so these are our marginal products of capital and marginal products of labor. If the rental price of capital is 20, what is the wage rate? So we can now look a little bit about, we can go into just a little bit about the efficiency here between these products. So essentially we could look at 50 K to the 1/2, L to the minus 1/2 over 25. And we want to see if this should be equal to 50 K to the minus 1/2, L to the 1/2 over 100. And so in order to get the relationship of equality here, we can solve this down in a little bit. So what we're end up getting is 2K to the 1/2, L to the minus 1/2 is equal to 1/2 K to the minus 1/2, L to the 1/2. Here we can simplify a little bit more. I'm going to multiply both sides by 2 so that we get 4 K to the 1/2, L to the minus 1/2 is equal to K to the 1/2, L to the 1/2. And so what I'm going to do now is divide both sides by L to the minus 1/2. So I get 4K to the 1/2 is equal to K minus 1/2 L to the 1/2 divided by L to the minus 1/2. We simplify this again, so we get K to the minus 1/2 L to the 1/2 times L to the 1/2. So we get 4K 1/2 is equal to K to the minus 1/2 times L. We're going to do the same thing with K to the minus 1/2. So I get 4K is equal to L. So now we have a relationship between K and L that maintains the equality that we just found for our optimal level of inputs. So I think this is a good problem to kind of work through here. We kind of took a roundabout way of answering some of the questions here. And so I urge you to kind of look at more of these marginal products a little bit. So essentially what we did is created a relationship here in this problem between K and L. And I think that's important. What we've done essentially is by essentially maintaining the equality here, what we've done is said that we know with every capital and labor combination, what maintains that equality. So essentially what we're saying here is, given this scenario, let's make this a little bit better here. So if we want to draw our essentially isoquant and isocost curve, just imagine that that's tangent, and then we move out our isocost curve, something like this. What we do is maintain our tangency that way. Or if we move in our isocost curve, we can maintain our tangency this way, something like this. And so what we've seen, this relationship 4K is equal to L maintains that. So what would we call this? This is what we call an expansion path. So this expansion path is the equality between the marginal product per dollar spent on capital and labor, which creates an important set of points that represent efficiency for the firm. So the expansion path is the locus of points for which the isocost and the isoquant curves are tangent. Represents the cost minimizing, profit maximizing combinations, capital and labor for different operating budgets. So what is our essentially expansion path? It's this line right here. We realize that there's points all on this line that equate to different tangencies between different budgets and isoquants. But all the points on this line represent or maintain the equality of the slope of the budget constraint or our isocost to the slope of our isoquant. And so we can see that again, this expansion path, what that looks like, but we've created it here. And so we can do, again, kind of a similar problem for this. So suppose we're given this production function. Suppose that we have Q is equal to 30, K to the 0.7, L to the 0.5, where input prices are 20 and 30 respectively, determine the expansion path. In order to do that, the equation of the expansion path must be in terms of K and L. So we want to start with the marginal product of capital divided by the price of capital, and that must be equal to the marginal product of labor divided by the price of labor. So let's start solving for these things. We know that dq dk is going to equal 30 times 0.7 k to the negative 0.3 times L to the 0.5. dq dl is going to be 30 times 0.5 k to the 0.7 L to the minus 0.5. So we can start with dq dk, dq dl, and now plug these in so that we have 30 times 0.7 k to the negative 0.3 L to the 0.5 divided by the price of capital, which is 30. That's going to be equal to 30 0.5 k to the 0.7 L to the negative 0.5 divided by the price of labor, which is 20. So we're going to notice some things start canceling here, and we're going to be able to rearrange this. So let's cancel out the 30s really quickly here. we notice that we have, this is essentially, we can rewrite this to 0.7, essentially L is equal to 3/4 K. So that we can rewrite this again, so that we have 7/10 times 4/3 L is equal to K. So that we have 28/30 L is equal to K. So this is the equation of the expansion path. Good. So we can continue going, we can continue looking at some more problems here. So for us, the problem 7.5. Muckrakers is a cable television industry construction contractor that specializes in laying fiber optic cable. Muckrakers lays fiber optic cables according to the following short-run production function. So what we have is Q is equal to K 5L minus 1.25 L squared. We have a K is hours of excavating equipment, which is fixed at 200 hours. The rental price is the same for both labor and capital at $25 per hour. So P sub L is equal to 25 is equal to P sub K. It has received a offer from Telecablevision to install 1,000 meters for a price of $10,000. Should Muckrakers accept this offer? And I think this is an interesting problem to go about solving here. We can begin solving this problem by plugging in some of the things that we know here. So what we know is essentially that we want to create 1,000 units of length of fiber optic cable laid, and that we're going to use 200 hours of capital. So then that we have 5L minus 1.25 L squared. And so essentially what we could do is start solving for this L. So we could divide both sides, so we have 5 is equal to 5L minus 1.25 L squared. So let's set this equal to 0 is equal to negative 5 plus 5L minus 1.25 L squared. So now we could solve using our formula, the opposite of B, plus or minus the square root of B squared minus 4AC all over 2A. Using our quadratic formula here so that we have negative 5 plus or minus B squared, so 5 squared minus 4 times negative 1.25 times negative 5 all over 2 times negative 1.25. So we solve this down and we find that L should be equal to 2. So now we have L is equal to 2 here. And so we could essentially look at our budget to see how much it'll cost us to make this fiber optic cable. So we know the total cost is going to be 25 times 2 plus 25 times 200. And what we know is that this value should be essentially this value should be less than 10,000. So we should indeed take this. We should indeed take this offer, and it's a good one, right? Because we're essentially making a lot of money on this. So it cost us $10,000, but it cost us $5,050, but we're getting $10,000. And then the second part of this, does the production function exhibit constant increasing or decreasing returns to scale? Again, we know how to solve that. Let's look at our production function again. And let's set K and L equal to 1. If that's the case, then we're going to have 1 times 5 times 1 minus 1.25, 1 squared. And we should get 5 minus 1.25. That's going to be equal to 3.75. So then let's set K is equal to L is equal to 2. And so let's have Q is equal to 2 times 5 times 2 minus 1.25, 2 squared. And we can solve this down to get 2 times 10 minus 5 here. So that we get Q is equal to 10, and so that we have increasing returns to scale. Okay, so now we're going to finish here problem 7.6. This is something I wanted you guys to try on your own, but we're going to try it together here. So now part A asks, what is the optimal capital labor ratio given this is our production function, Q is equal to 250 L plus 4K, and given that we have the price of labor, P sub L is equal to 25, and then we have P sub K is equal to 100. So what we could start doing again is creating our equality between the marginal product of capital and marginal product of labor. So we'll take our partial derivative with respect to L, we get 250, and then we can essentially have our marginal product with respect to capital, and so we should get 1,000. And now we can set these equal to each other. So we have marginal product of capital 1,000 divided by the price of capital 100, and that should be equal to the marginal product of labor divided by the price of labor. And lo and behold, what we end up seeing is that these are indeed equal to each other, that we get 10 on both sides. And I think this is an interesting result here. We have nothing in terms of capital and labor. So really what we're saying here is that any inclusion of capital and labor is going to give us our optimal amount. And the reason we know this essentially is because this production function is linear. If we were to create an isocost and an isoquant, we would notice that our isocost line essentially is the same as essentially our isoquant. It would look like this. They would overlap on each other. And so if that's true, then every point on this line is going to be efficient. So it's interesting. It's a little bit different here than what we've seen before, but I think it's a good exercise. So part B says, suppose the price of capital were lowered to $25 per hour. What is the new optimal ratio of capital to labor? Well, we can go back to kind of what we've done so far, and our marginal product of both capital and labor are not going to change. The only thing that we're changing here is essentially that we are going to now create 100 divided by 25 is equal to 200, or sorry, 1,000 divided by 25 is equal to 250 divided by 25. And so what we end up getting is not an equality, but we get 40 is essentially greater than 10. So now I think this is interesting, because this was now we don't have an equality. But what we're saying here is that for all instances, capital is more efficient for us. So essentially, we should just only use capital. We should only use capital here. Because we shouldn't trade off between any labor, and our efficiency lies with just using this capital. So this is called a corner solution. It doesn't happen often, but it can happen. And I think this was a good problem. So we can move on now to the idea of unconstrained optimization of profit. And I think this is a good idea. What we have here is looking at profit in a variety of contexts. So what we're going to start looking at is understanding that profit is going to be the difference between total revenue and total cost. And so we're going to first define it simply as a function of Q. And if that's the case, what we could do is look at some mathematical ideas behind profit. The first is being, what does that first derivative tell us? So let's define this and take our first derivative. And what we end up having here is that our first derivative is the essentially the derivative of total revenue divided by with respect to quantity minus the change in total cost divided by the change in quantity. And so what we know here is that we have marginal revenue minus marginal cost equal to 0 because we're looking at the maximum here. And so if this is true, then it means that marginal revenue must be equal to marginal cost. And I think that's a good result because it coincides mathematically with the intuition we've learned in principles classes that almost all firms, I should say, in every market are looking for the point where marginal revenue is equal to marginal cost. So to ensure that this is a maximum, again, we want to verify this happens. So we'll take the second derivative, and the second derivative is going to be less than 0 if that the change in the total cost curve, essentially that the change in marginal cost is greater than the change in the marginal revenue. And that kind of, again, coincides with our intuition that as we continue to essentially create more and more goods, diminishing marginal product takes over and costs rise more than total revenue does. So we can start solving or looking at the problem 7.7 here. So what we find in 7.7 is that we're asking a few different things. So we have this profit equation. So profit is equal to negative 2,000 plus 450Q minus 50Q squared. So at what output level is profit maximized? What I would say is we need to first take our derivative with respect to Q then. So we get 450 minus 100Q is equal to 0, so that we get 4.5 is equal to Q for part A. And so we know that that has to be true through our mathematical result. And so B, what is Squaple's marginal profit function? Well, the marginal profit function is just marginal profit is equal to 450 minus 100Q. That's it. This is our marginal profit equation. So what is Squaple's marginal profit at the profit maximizing level of output? Well, for us, this is part C then, for us, we're just going to plug this in. So what is marginal profit at 4.5? Well, we have 450 minus 100 times 4.5, which is equal to 0. And to us, that makes a lot of sense because we've maximized profit. There's no other quantity that's going to give us an additional profit. So the marginal profit should be 0 here. And then if we go to 3, we see 450 minus 100 times 3, which is equal to 150. And so we see that if we were to produce the third unit, we would get an additional profit of $150. So what output level is marginal profit optimized? So let's take the second derivative. So we want to take the derivative of marginal profit with respect to quantity, which is equal to the second derivative of our profit equation. And so we have negative 100. So negative 100 is essentially our output level where profit is essentially maximized. Marginal profit is equal to 0. So what then is our average profit function? Well, again, we're going to take our original profit function and divide by Q. So we have pi divided by Q. So this is going to be average profit. And that'll be negative 2,000 divided by Q plus 450 minus 50Q. And that's our average profit equation. So where is it optimized? So d pi q dq is equal to 2,000 over q squared minus 50 is equal to 0. So we can solve this down so that we have essentially 2,000 divided by 50 is equal to q squared. So 1950 is equal to q squared. Square root of 1950 is equal to q. So at this quantity, we would find a positive value, which would essentially, for us, we would find essentially the optimized level of our average profit function. Do we know, would this essentially be positive or negative? Well, or a minimum or a maximum. In order to identify that, we can take our second derivative. So we have negative. So we have negative 4,000 over q cubed. And so this is going to be essentially less than 0. So we know that our first derivative set equal to 0, second derivative less than 0. We should actually have a maximum here. And that kind of makes sense to us because we're talking about profit levels. Good. And so we didn't essentially finish part G. And this is something that I wanted you to do on your own. And this was looking at the relationship between marginal profit and average profit. And so I want you to kind of perform this exercise. Again, I think it's a good one. So we now can look at under very, very specific circumstances of competition levels. So we're going to start with perfect competition. Recall that under perfect competition, prices are set by market forces, and firm takes those prices as given. And essentially what we find, what comes out of this, is that prices being fixed to some level gives us some really interesting information. That if I want to look at what is the marginal revenue, so we have total revenue is equal to P sub naught Q, and I want to know what marginal revenue is, so DTR DQ. Well, I get marginal revenue is just our prices. And if I want to look at average revenue, total revenue divided by Q, so P sub naught over Q divided by Q, well, I get P sub naught. So we know that marginal revenue is equal to average revenue is equal to P sub naught. So what we could do is substitute this into essentially our profit maximizing condition, because we knew that marginal revenue was equal to marginal cost. So here we know that P sub naught is equal to marginal cost. And that's good information for us in terms of solving for the profit maximizing level of quantity. What we would also suspect in this instance then is that the change in marginal cost should be greater than 0 in some way. But we're not too concerned with the second derivative here. Firms should choose a quantity where the price is equal to the marginal cost. We know that at the profit maximizing level of output, total cost is increasing at an increasing rate. And again, that is intuitive to us where marginal profit is 0 and falling. And again, this is not specific to perfect competition, but for all profit maximization. So graphically, what does this look like to us? So what we see here is what we have is the firm's demand curve. So the firm essentially sees this elastic demand curve where marginal revenue is equal to average revenue is equal to demand is equal to price sub naught. And what they do is identify this point. They identify this point B and get Q star, because that's where marginal revenue is equal to marginal cost. And so Q star is really important because it tells us some things. So this Q star tells us for our profit function, at Q star, we are maximizing profit. And we can see that happens at point B. And then if we're looking at the difference between total revenue and total cost, what Q star tells us is that we're finding the largest difference or the largest gap between total revenue and total cost. Right? That largest gap, that is the maximization. So that occurs right at Q star. Okay, so how about a problem here? So problem 7.8. 7.8 tells us that we have total cost, which is equal to 6 plus 33q minus 9q squared plus q cubed. So now, what is the firm's total revenue function? So we're perfectly competitive. So total revenue is going to equal the P sub naught times Q. So total revenue is going to be equal to 18 times Q, and this is our total revenue function. What is the marginal revenue? Marginal revenue is DTR dQ, which is equal to 18. Marginal cost is going to be that first derivative, DTC dQ, which is equal to 33 minus 18Q plus 3Q squared. So this is going to be essentially our marginal cost. And then the average total cost equations. So average total cost is equal to total cost divided by Q is equal to 6 over Q plus 33 minus 9Q plus Q squared. Okay, so we're not going to diagram this, but our total profit equation then becomes 18Q minus our total cost function, which is 6 plus 33Q minus 9Q squared plus Q cubed. And so if we're going to optimize this, we want to look at d pi dq. So we are going to find that it is 18 minus 33 plus 18q minus 3q squared. We're going to set that equal to 0 so that we get 15, negative 15, plus 18q minus 3q squared is equal to 0. And then we could use our quadratic formula, the opposite of b, plus or minus b squared minus 4ac all over 2a. We can plug in our values so that we have negative 18 plus and minus 18 squared minus 4 times negative 3 times negative 15 all over 2 times negative 3. And we could solve that out, and this will give our profit maximizing output level. And again, remember that if you're getting a few values, for profit, we saw that profit looks like this in some way, and that we could actually indeed have a minimum for profit, and then we could have a maximum for profit as well. So you just want to double check. What I would do once you find these values is plug them back into your profit equation, and then you can determine from there what is actually your maximum profit. Okay. So we can also look at perfect competition and maximizing profits in a slightly different way, and that is through essentially looking at substituting out quantities for capital and labor. So we know that Q is equal to F of K and L, and we know that we have total revenue is P sub naught times Q, essentially minus this total cost. So what we could do is plug in the values that we know, that profit is going to be equal to P sub naught times F of K and L, and we know that total cost is going to be P sub L, L minus P sub K, K, so that we can actually find these first order conditions for ourselves. So what we end up knowing, or what we end up getting here, is when we take our first order conditions, is that we have P sub naught times the marginal product of capital minus the price of capital is equal to 0. And then we have the price times the marginal product of labor minus P sub L is equal to 0. So what do these actually tell us? So it tells us that our resource prices, P sub K and P sub L, our marginal resource prices, essentially have to be equal to essentially the marginal revenue product. for both goods. So intuitively think of the first order condition to be the equality of marginal revenue product of the input and the rental price of the input, or marginal revenue cost. So we have this equality happening here. So we interpret this condition to mean that firms will hire or use an input up until the point where additional revenues precisely equal the cost of hiring that additional input or using that additional input. And I think that's some solid intuition. So we can kind of move forward and solve another problem here. So we have 7.9. So now we have Q equaling K to the 1/2, L to the 1/2. So the firm can sell all of its output for $4. So the price is equal to 4. The price of labor and the price of capital are $5 and $10 respectively. So the price of capital is equal to 10. Price of labor is equal to 5. It says determine the optimal levels of capital and labor usage if the firm's operating budget is 1,000. So there's a couple things that we can actually do here. What we could actually do is use what we know with our optimality. So we could talk about the MPL over P sub L is equaling MPK over P sub K. So we could do, let's do that. So we have dQ dL, which is going to be equal to 1/2 K to the 1/2 L to the minus 1/2. Then we have dQ dK, which is going to be equal to 1/2 K to the minus 1/2 L to the 1/2. And so we're going to set this equal to each other with our prices respectively, so that we have 1/2 K to the 1/2 L to the minus 1/2 over 5, and then we have, it's going to be equal to 1/2 K to the minus 1/2 L to the 1/2 divided by 10. And so we can continue to solve down here, so that we get that the 1/2s cancel, so we have 10K is equal to 5L, so we have 2K is equal to L. So then our next step would be to look at our operating budget, which is 1,000, which is equal to P sub L times L plus P sub K times K. So we have 1,000 is equal to P sub L is 5 times L plus 10 times K. But we already know L in terms of K, so let's do 1,000 is equal to 5 times 2K plus 10 times K. So if 1,000 is equal to 10K plus 10K, so we have 1,000 is equal to 20K, which we get 50 is equal to K. Good. So now we have a level of capital that is going to essentially be efficient for us. So then what amount of L do we need? So we have 2K is equal to L. So we'll put stars here so we know that these are the optimal levels. So that we have 2 times 50 is equal to L. So 100 is equal to L star. Good. So now we have our 2 optimal levels. So now what is our essentially our profit maximizing level, profit at this optimal level? So we have profit is equal to total revenue minus total cost. So we don't know yet how much we're actually making, but we can. So we could do Q is equal to K to the 1/2, L to the 1/2. So we have Q is equal to 50 to the 1/2, 100 to the 1/2. And so that we can calculate this out so that we have essentially 50, square root of 50 times 10. And we get 70. The amount of quantity that we get is essentially 70.71. Okay, so now we have profit is equal to 4 times 70.71 minus the cost of producing. So essentially we know the cost is going to be, the operating budget is going to be 1,000. We could have also put this in. So profit is equal to 4 times 70.71 minus 5 times the amount of labor we use, 100, minus 10 times the amount of capital we had, 50, and so now we are going to get profit is equal to our total revenue, which is going to be 282.84 minus 1,000, which we get negative 717.16. Okay, good. So we've now solved out, and this is our profit maximization. So we have economic profit. So essentially this was a profit minimization problem. So we're looking at essentially loss minimization, I should say. The other way that we could solve this problem, and I could ask you a question like this, and that would be, how do we know that this is optimizing? And so we're going to loop back around at the end of this discussion and come back to 7.9 and solve this problem in a slightly different way. And we're going to talk about how we know that this is the optimal level. But intuitively, as we kind of work through this, we know this has to be the optimal level, and it has to be profit maximizing or cost minimizing in some way. And so now we switch gears to a different industry, and the industry here is monopolies. So again, let's assume that total cost is an increasing function of output. So for the monopolist, the selling price is a function of output. So now we're creating a demand curve here. So P is equal to P of Q, means that we have prices in terms of quantity. That's our demand curve. So now profit equation becomes pi of Q is equal to P of Q times Q minus total cost, which is a function of Q. So now everything's still a function of Q. And so we can take our first and second order conditions, but to simplify this, we assume again that the demand is going to take a linear form, so that our demand curve, P is equal to A plus BQ, is going to be substituted in for what we know. And if that's true, then what we see is that we again have this idea that this is our marginal revenue. This is our marginal cost. How do we know it's marginal revenue? If we were to graph this relationship with demand, this would be our marginal revenue curve, and the slope is twice as steep as essentially our demand curve is. Okay, so we have the picture for this. Again, what we're doing is equating marginal revenue with marginal cost. That happens at Q star. But now the difference is that we go up to P star, or go up to our demand curve in order to determine P star. So P star is not given to us. So we actually have to solve for Q, take Q, plug it into the demand curve, and then we are going to get our price out of this. And essentially we see the same profit function where we're maximizing profit at Q star. And again, we go up to Q star and we're looking at the difference between total cost and total revenue, and that's going to be its widest point. So let's solve a problem from this. So this is problem 7.10. So 7.10 says the demand and total cost equations for the output of a monopolist are Q is equal to 90 minus 2P. So we have Q is equal to 90 minus 2P, and that we have total cost is equal to Q cubed minus 8Q squared plus 57Q plus 2. So find the firm's profit maximizing output level. Knowing that we have a demand curve, this has to be a monopolist in some way. So the first thing that I'm going to do is solve. I'm going to take our demand curve and I'm going to solve for P in terms of Q. So I have Q minus 90 is equal to negative 2P. So then I can divide everything by negative 2. So I have negative 1/2 Q plus 45 is equal to P. So that's 45 minus 1/2 Q is equal to P. So now our profit equation, profit is equal to total revenue minus total cost. I can plug in some values here. I know that profit is going to be equal to Q times 45 minus 1/2 Q minus Q cubed minus 8Q squared plus 57Q plus 2. So let's do the first derivative, d pi dq. So I get 45 minus Q minus 3Q squared plus 16Q minus 57Q equal 0. So now we have some cleanup to do here. So we can combine some terms. So we can have, we have negative 57 plus 16 minus 1Q. So we have 45 minus 42Q minus 3Q squared is equaling 0. So now again we can solve with our quadratic so that we have opposite of b plus or minus plus n minus b squared minus 4ac all over 2a. We can plug some values in. Minus 42 plus or minus square root of 42 squared minus 4 times negative 3 times 45 all over 2 times negative 3. And when we solve for that, I'm just going to sneak a peek at the solutions here. And so we solve for that, we get Q is equal to 1 and 4. So we have Q is equal to 1 and 4. So now what we have to do is determine what is the higher profit for us. So we can plug 1 and 4 back into our profit function. So we have profit is equal to 1 times 45 minus 1/2, 1 minus 1 cubed minus 8, 1 squared plus 57 times 1 plus 2. So that we get 44.5 minus 1 minus 8 plus 57 plus 2. So that we get 52 minus 52. So we know that this is less than 0. So now let's plug in 4. 4 times 45 minus 1/2 times 4 minus 4 cubed minus 8 4 squared plus 57 times 4 plus 2. So now we have some work to do here. So essentially we have 43 times 4, which is 172, minus 4 cubed, which is 64, minus 4 squared times 8, which is essentially 64, which is, 128, plus 57 times 4, 228, plus 2. Okay, so now we could add this up. So we have 64 minus 128 plus 228 plus 2. So we get 166. So we have 172 minus 166. And so we know that we've solved for a positive profit of 6. So good. We know that then 4 is going to be our profit maximizing level of output. Determine the price per unit output, which the profit maximizing output is sold. So at a Q of 4, we now go back into our demand curve where P is equal to 45 minus 1/2 times 4. So if P is equal to 43. So this is our price per unit sold as monopolist. Good. So then we have another problem. 7.11. So suppose that we're given this demand function, and suppose further we have a total cost function of T2Q squared. Find the output level that will maximize profit. So in order to do that, we need profit is going to be equal to P in terms of Q times Q minus total cost in terms of Q. So let's solve for that. So let's multiply. So we have Q is equal to 20 over 3 minus 1/3 P. Let's multiply everything by 3. So we get 3Q is equal to 20 minus P. So we have P is equal to 20 minus 3Q. Let's plug in to profit. Profit is equal to 20 minus 3Q times Q minus 2Q squared. So let's take our first derivative with respect to Q. So we have 20 minus 6Q minus 4Q is equal to 0. So that we have 20 is equal to 10Q, so that 2 is equal to Q. So that is our profit maximizing level of output. So what is our profit at 2? So we can plug this in. So profit at 2 is equal to 20 minus 3 times 2 times 2 minus 2 times 2 squared, which is equal to 20 minus 6 times 2 minus 8. So we have 14 times 2 minus 8, which is going to be 28 minus 8, which is 20. Good, so we've already solved for A and B. What is the monopolist average revenue function? So if we want average revenue, total revenue is going to be 20 minus 3Q times Q. So average revenue is equal to total revenue divided by Q. So we have 20 minus 3Q. That's our average revenue function. Determine the price per unit at the profit maximizing level of output. So we found that Q is equal to 2. So P is equal to 20 minus 3Q. So P at P star and Q star, we have 20 minus 3 times 2. So that we have P star is equaling 14. So that is our price per unit at the profit maximizing level of output. So now part E says, suppose that the monopolist was a sales, so total revenue maximizer. Compare the sales maximizing output level with the profit maximizing output level. So if we're maximizing total revenue, so total revenue is equal to 20 minus 3Q times Q. So now let's look at the first derivative with respect to Q, so that we have 20 minus 6Q is equal to 0, so that we have 26 is equal to Q. And this is bigger than 2, what we found out before. So we could look at the price that we would charge at this quantity. So we could do P star is equal to 20 minus 3Q star. So we have P star is equal to 20 minus 3 times 20 over 6. So we have P star is equal to 20 minus 10. So P star is equal to 10. So now we have higher quantity but lower prices. And that makes sense for us graphically. So if we think about this, and so if we are going to look at a marginal cost curve, which is linear, we now have this being Q star. This is our monopolist, and this is our price. Right, so this is 2 and 14. And now what we're doing is essentially not taking marginal revenue, but we're lowering and we're getting to 10 and something greater. So we have 10 here, and then we have 26th. Okay, so let's move on to the last part of our lecture here, and this constrained optimization of profit. And so for us, constrained optimization is going to be very similar to what we did with the Lagrangian at the beginning of class. And that's it, really. So here we're going to construct a Lagrangian method of optimization, looking at firm-specific resources. So we went through a very just simple explanation that we're going to have some demand curve for a firm, and we could have some cost curve for a firm. But what we want to do is, given the demand curve, given the cost curve, what we want to say is, what are we constrained by in this instance? So in this example, we're saying that we're constrained by having a budget, and that budget is going to be determined by how much we choose of our input times our input price. So really, our constraint in this instance is indeed our budget constraint. So here we're maximizing our profits by looking at the difference between total revenue and total cost, subject to our constraint. So in order to do this, we need to set up a Lagrangian, and we know how to do that. So we create a brand new function, this Lagrangian function, and what we do is include our function we want to optimize, and we include essentially this new shadow price value lambda and the constraint. So in order to do this, we have to set our constraint equal to 0 before it's included into the new function. So here we're trying to maximize a function. So we're maximizing f of k and l, subject to g of k and l is equal to some k value. So now what we're doing is essentially creating this this Lagrangian is f of k and l. And what we're going to do is set this equal to 0, so plus lambda times k minus g of k and l. And so now this is our Lagrangian setup, and now we can take the first derivative. So we could do dl dk, which is equal to 0, dl is equal to 0, and then dl d lambda, which is equal to 0. So now we have our set of equations that we can now use to solve for our three values. So here's another problem, 7.12. So we have a total profit equation. So we have profit, x and y, is equal to negative 1,000 minus 100x minus 50x squared minus 2xy minus 12y squared plus 50y. So now x and y represent the output levels. Part A says use the substitution method to determine the profit maximizing output level of x and y, subject to the side condition that the sum of the two product lines equals 50 units. So we have subject to x plus y is equal to 50. We're going to skip the substitution method. We're going to go straight to the Lagrangian multiplier method. So we're going to set up this Lagrangian L. So this Lagrangian is negative 1,000 minus 100x minus 50x squared minus 2xy minus 12y squared plus 50y plus lambda 50 minus x minus y. So now we can take our first derivatives. So we'll take the partial of our Lagrangian with respect to x. So we get negative 100 minus 100x minus 2y minus lambda is equal to 0. Take our partial of the Lagrangian with respect to y, so that we get negative 2x minus 24y plus 50 minus lambda is equal to 0. And then, as always, when we take the partial of the Lagrangian with respect to the shadow price lambda, we're going to get back our constraint, 50 minus x minus y is equal to 0. And so right away, what we could do is use, since these are all set to 0, we could right away eliminate lambda because there's no values in front of lambda. So we can have negative 100 minus 100x minus 2y is equal to negative 2x minus 24y plus 50. So let's start simplifying here. So I'm going to bring some y's over and some x's over so that I have essentially 22y is equal to 98x plus 150. And so now I can divide everything through by 22. So we have 98 divided by 22x plus 150 divided by 22. So now what we're left with is our last constraint. So now we have 50 minus x is equal to 98 over 22x plus 150 divided by 22. And so now we can solve down for this for x. And I'm going to skip to the solution. And so when we solve for this, we get x essentially should be equal to 7.92, which means that y, when we plug our x value back into our constraint, should be equal to 42.08. And then when we plug both our values for x and y into one of the values to solve for lambda, or one of the first order conditions to solve for lambda, we get negative 975. So now what we have is to interpret this value of the shadow price. So what we're saying here, essentially, in this value of our shadow price, lambda star is indeed the change in our Lagrangian if we're able to change this value k. K is some parameter that we've chosen. In our instance, it was 50. 50 was equal to k. So now, if we're able to change this k by a little bit, and essentially what we're maximizing here was profit. So how does profit change as we change k? We know that it's going to change by 975. So what we say is, if we were to reduce the amount of output we make by 1 unit. So if we go k from 50 to 49, profit will increase by $975. That's how we interpret this shadow price here. That's what we say intuitively. Okay, and so as I said before, we're going to go back to a problem that we saw previously and try and solve it in a slightly different way. So I'm going to try and find it here. I believe it was 7.9. And so now we are faced with, again, this problem 7.9 with constrained optimization. So let's write out what we found out before. We know that essentially the values that we had, and I think they're different from the book solutions, and I think ours are actually accurate. So 7.9, we found that K star is 50, L star is 100. So we found K star is 50, L star is equal to 100. So could we have solved for this in a slightly different way? So let's see. Okay, so we go back to problem 7.9, and the production function facing the firm we have is essentially Q is equal to K to the 1/2, L to the 1/2. We know that the price that they're selling piece of knot is 4. We know that the price of labor is equal to 5, and that the price of capital is equal to 10. So can we solve 7.9 with constrained maximization? I think we can. We also know that the amount of our total cost essentially can exceed $1,000. So we have a few things happening here. We know that TC naught is 1,000. We can solve for total revenue. Total revenue is going to be equal to P sub naught times Q. So that's equal to 4 times K to the 1/2, L to the 1/2. We also know that we're constrained by the 1,000 has to be equal to 5L plus 10K. So we have total revenue, total cost, and a constraint. So let's put all that together in terms of a constrained profit function. So we're going to look at the Lagrangian, which is going to be equal to 4 times K to the 1/2 L to the 1/2 minus 1,000, subject to, we put in our shadow price, 1,000 minus 5L minus 10K. So now we can take our first derivatives with respect to LK and lambda. So partial L, partial K is going to be equal to 2K to the minus 1/2 L to the 1/2 minus 10 lambda is equal to 0. Partial L is going to be equal to 2K to the 1/2 L to the minus 1/2 minus 5 lambda. And we'll take our partial of the Lagrangian with respect to our shadow price so that we have 1,000 minus 5L minus 10K is equal to 0. So now we can do some algebra. So I'm going to take our first equation and I'm going to divide by 10 and set equal to lambda so that I have lambda is equal to 1/5 K to the minus 1/2 L to the 1/2. Then I'm going to take our second equation, divide by 5, and set equal to lambda. So I have lambda is equal to 2/5 K to the 1/2 L to the minus 1/2. I'm going to set these equal so that I have 1/5 K to the minus 1/2 L to the 1/2 is equal to 2/5 K to the 1/2 L to the minus 1/2. I'm going to solve. I know that we have like denominators, so those cancel. I'm going to bring K, so these cancel with this. I'm going to bring K to this side. I'm going to bring this L to this side. So I have L is equal to 2K. So now we have our last constraint. So we have 1,000 is equal to 5L plus 10K. So I know 1,000 is equal to 5 times 2K plus 10K. So I know 1,000 is equal to 10K plus 10K. So 1,000 must be equal to 20K, which tells us that K must be equal to 50. That's exactly what we found before. We had K was equal to 50 up here. So now let's plug in for L. So we know L star has to be equal to 2 times K star. So L star is equal to 2 times 50. So that we have L stars being 100 and K stars being equal to 50. That's great. So now we've solved the exact same for the exact same solution that we did before. So when we first solved 7.9, if you recall, we did so through looking at strictly the optimization or the optimal amounts. So we first solved by looking at MPL over PL is equal to MPK over PK, and then from that, this solution we plugged into our constraint. So we found that constrained optimization and this optimal level of capital and labor gives us the same thing. This is the proof that shows us that profits must be maximized in this way. But we do have the last little bit of information, and that is the shadow price. And so now what we have is shadow price, which is equal to, we could do 1/5 K to the minus 1/2 L to the 1/2. So now we can do lambda is equal to 1/5 50 to the minus 1/2, 100 to the 1/2. We can rewrite this a little bit so that we have 1/5 100 divided by 50 over to the 1/2. So we have lambda is equal to now square root of 2 over 5. So good, we have now a value for lambda that we can talk about in terms of the shadow price. This is lambda star. And that was it. That's it for all of our constrained optimization. We didn't do many problems in class. We did one in class and one extra one here in this lecture. I would urge you guys to look back through your quizzes and your tests and your homework to solve other constrained maximization problems, just so that you are remembering how to do this. Okay, good luck studying here, and we will talk to you next time.